All right, this is your alternate to the Unit 3 seminar since we won't be having one. Hopefully you're having a Merry Christmas break. So Unit 3 is Applied Data Analysis, meaning you're actually going to take the information that we learned from Unit 1 and 2, and we're giving you an assignment where you're going to have to actually understand that information that you had and give it back to us in a report showing that you do understand. So that first assignment is worth 100 points. This is the same as the exam. And we just want you to focus on this assignment. So there's no assigned reading, there's nothing else to turn in, no seminar or anything. And again, like I said, this is the first application of your understanding of the reading that you've gone through. So you're going to refer back to the reading in Unit 1, Unit 2, and also the information I have given you in the seminars and in this seminar to make this assignment. Now, what the assignment is, what we're asking you to do is use the Kaplan Library to find a peer-reviewed study. So this is a scientific study where they do statistics, and it should be published in a scientific journal. So not a blog, not a website with information. It needs to be a scientific study. And if you need help with that, you can email me, or if you want me to check on something, or if you want to check on what you have picked out, you can email it to me and I'll say whether it's a good article or not. Now, we want you to pick a study that has done one of the analyses that we've gone over in your reading or in seminar, and we're going to go through a couple of those today as well. What you're going to do in the report is describe the test. So just like we did in seminar, describe the scenario, what's their question, where they got their data, and then you're going to talk about the statistical test that they did and how it applied to the study. If you break things down into smaller steps and use those as headings, those will organize it and make it very easy to do. Now, there's not a lot of writing; it's just one page, so it shouldn't be too much work. The big work is going to be reading and understanding the scientific article that you pick out. The requirements for the paper are going to have one double-spaced page of writing. You'll need a title page and you'll need a references page. Everything needs to be in APA format. It needs to be 12-point font Times New Roman. And you should have legit references, so no .com websites. You'll need to reference your book. If you use information from the book, make sure that you paraphrase, use information in your own words. You'll make sure you need to reference the article you picked out. So you're going to have a literature cited with at least that one article, but also you can supplement it with other articles if you need to. You should also have a viewpoint, so basically just show your understanding of the material. And I will check for plagiarism by using the Turnitin software, plagiarism software that was provided by Kaplan. So make sure that you put things in your own words. All right, that's the assignment. I'm also going to go over a couple scenarios which highlight two more statistical tests, a correlation and linear regression. So let's go back to our research physician examples that we've given in the other seminars. So let's say, again, we're looking at symptoms of the flu and we have some data. And one of the questions we've been asking our patients is how often that they wash their hands. And we want to know if washing your hands has any correlation or any association with how quickly they recover. So the variables we're going to look at are how often somebody washes their hands and how many days it takes for them to recover from the flu. Both of these are continuous variables, so they aren't categorical. They don't put it into we could say split into people that wash their hands and people that don't, but we're not. We want to know how many times a day they wash their hands. So both of them are continuous, and because we want to know their relationship, we're going to use a correlation test. Okay? And a correlation can be positive, negative, or you can have no correlation. This is a scatter plot. Those lines show the line that best fits those data points, which are the x's. If it's a positive correlation, that means in our instance, it would be if the people who wash their hands more take a longer time to recover. A negative correlation, which is probably what we think is going to happen, is the more people wash the hands, the less amount of time it's going to take to recover. And if it's just random, if it has no association, then it would look like that one to the right. So again, you can see here's some more data points. This is from the book. The one on the left would be a positive correlation. The one on the right would be a negative correlation. Now, the way that correlation is displayed is using what's called the correlation coefficient, which is represented by a lowercase r. And a -1 is a perfect negative relationship. And that's not going to ever happen. You're never going to have a perfect relationship if you're dealing with real data. There will always be some variation. +1 is a perfect positive relationship, and you also never have that. But the r will be somewhere between 1 and -1, okay? Which is also representing the slope of the line. Okay, a strong relationship is going to be closer to 1 or closer to -1, and a weaker relationship will be closer to 0. The coefficient of determination is just the correlation efficient r squared, and it's called r squared. And this tells us how well the variable is associated with the other one, or how much variation can be explained by each of the variables by looking at the other variable. The test we use is called the Pearson's R test, and it calculates a t-value, which then can be used to calculate a p-value, which is our significance. Once again, we've talked about alpha last time. We're going to set the alpha at 0.05. And our null hypothesis is that r equals 0, which would mean that there is no relationship between the two variables. The alternative hypothesis is that r does not equal 0. And this is a two-way hypothesis. If we had an inkling, like I mentioned before, if we thought that it's going to be a negative relationship, then our alternative hypothesis would be r is less than 0. And if it was the other way around, it would be r greater than 0. So in our scenario, we collect data from 30 patients, and we do a Pearson's R correlation test. We're going to say it's a two-way test here, but if we had an inkling, like if we said, if we thought that it would be a negative relationship or positive, it would be a one-way test. This is what the actual data looks like, and you can see this is the graph. I didn't put in a line of best fit, but just by looking at it, you can kind of see, well, maybe it's positive, maybe it's negative. It's hard to tell. And when we actually do the test, we do have a positive relationship, 0.063, but it is very, very close to 0. So it's very weak relationship. And our significant value, or p-value, is very high. So nowhere near 0.05. What we don't have on this output from SPSS is the r squared value, but you can get it to print that out for you. So the coefficient of determination, you can just take 0.063 and square it. So the conclusion, based on our statistical test, would be something like this. The correlation between the number of days with symptoms and number of times hands were washed per day was positive but very weak and not statistically significant. R equals 0.063 and P equals 0.741. The coefficient of determination revealed that almost none of the variance in the number of days with symptoms can be explained by the number of times patients wash their hands. All right, that's correlation. If we want to see if two variables are associated with each other, we would use the Pearson's R correlation test. All right, so since washing hands wasn't correlated, we decided to look at some other variables. Only this time we want to see if we can predict when somebody will, or how many days it will take someone to recover based on a different variable. And the variable we're going to look at is blood glucose levels. So this is different from a correlation because we are looking at the ability to predict. And so whereas correlation was just whether they're associated with each other, now we want to know how well they predict. So the test we're going to use is called a simple linear regression. Excuse me. So the difference between this and the correlation is, again, that it's a prediction. We also get an equation, y equals bx plus a. It's very similar to y equals mx plus b, which you should have learned about when you took algebra. But basically, y is our variable that is being predicted. So in our instance, it's going to be number of days till recovery. And then x is the predictor variable, or also our independent variable. And in this instance, it's going to be blood glucose levels. B is the regression coefficient or the slope, so that is r. And A is the intercept or where it crosses 0. So you can see in this scatter plot here, we have a bunch of 10 points looking at education and income. The y-intercept, where the line crosses 0 to the very far left, is somewhere around negative 3.5. So that's going to be A. And then this line could be used then to predict income by looking at education. So if somebody has an education of 10, you go to 10, you follow that up to the line, and then you look to the left to see where it crosses with income. And you would say someone that has an education of 10 has an income of 3. So that's the power of simple linear regression and its predictability. So we got some data. This is what the data looks like. And you can already tell this looks like a pretty positive relationship between blood glucose and symptoms. But the actual test gives us a bunch of outputs. It gives us the r and the r squared value, which is very high, very positive. And the r squared is very high as well. It gives us a ANOVA test because that gives us the significance of the relationship, or p-value, and which is very low at 0.000 or less than 0.001. And then it also gives us the coefficients, or the what is needed to make the equation. So the constant negative 3.92 is the where it crosses the x-axis, and 0.085 is the slope. And so our equation is y equals negative 3.932 plus 0.85x. R squared is 0.864. The conclusion will look something like this, and I have a typo in here, so sorry. But a simple linear regression analysis was conducted to examine if blood glucose was a good predictor for number of days exhibiting flu symptoms. Blood glucose was a significantly positive predictor, and we have our R value and our P value, and it accounted for 86% of the variation, which would be the R squared value. And the regression equation was y equals and that should be negative 4.932 plus 0.05x. All right, so that's what linear regression is good for. There's also a test called multiple regression, where if we wanted to look at how not only blood glucose, but other health factors as well could help predict, we could maybe look at height, weight, hours of exercise, number of cigarettes smoked, all that stuff. We could do all these variables at once, and we could get a p-value for each of them to see which of them was significant and create a larger equation that had a stronger ability to predict how long it was going to take somebody to get well. All right, so what we've learned for these past few weeks is based on a study's question and the data available, they can run a variety of different tests. So if they're comparing two independent means, they're going to do the independent samples t-test. If they're comparing two dependent means or paired means, that would be the dependent samples t-test. If they're comparing three or more means, that's going to be the ANOVA, or analysis of variance. If they're testing for a between two variables, that would be a correlation. And if they want to see if two variables, or if one variable can predict another variable, then it would be a simple linear regression. And if you want to see if multiple variables can predict one variable, it would be a multiple regression. All right, so what we've learned from going through all these statistics is that they are very important. They allow us to check and see how well our studies are, or how well statistics are at predicting differences, and very important for doctor studies, drug studies, and the spread of disease. And they are used also commonly in all scientific studies where you're comparing groups or trying to predict. And so get excited for statistics, and we're going to have fun, and best of luck on your assignment.